Well, hello again, NATR 346, and welcome to the first of two 20-minute talks about stream flow and the hydrology of stream flow. And this is all part of Unit 4. And in Unit 4, you will find these two talks, as well as a couple of other nice references, not long, but they're very informative references on what I'm talking about today. There's also a couple of problem sets and further explanation of the material I'm going to cover. So please check those out. And then, of course, there's the obligatory quiz. You might not think it's obligatory, but there's also a quiz in Unit 4 to take. It's not timed and like same format as the other quizzes. So what both of these talks are about is stream flow and just a real basic introduction to how rivers work. The second part of the talk covers how rivers transport water. The first part is how again, just a basic introduction of how they transport bedload material. So that's what I want to cover here in the next few slides. So to do that, and again, I would encourage you to take an earth science or geography course or just read a book on physical geography if you're further interested in this topic. I'm barely going to touch it, but just to suffice to say that there is this phenomenon called the rock cycle. And the rock cycle, you could start it anywhere. It's like the hydrologic cycle. A lot of times the textbooks will start with the seafloor as being or part of the Earth's crust, and that seafloor, because of tectonic spreading and other processes, gets shoved underneath continental masses. And when it does that, it gets submerged deep in the crust where you can hit what's called the asthenosphere, and that earth material will then melt, literally. And once melted, there's a couple of pathways it can go. One, it can express itself in a volcanic form. Another more common way is that melted earth material will then solidify and crystallize as bedrock and many times get lifted up to form a mountain range. So in this cartoon, this would be like Mount Shasta, Mount Lassen, and Mount Hood, and actually the Sutter Buttes. And this cartoon here would be the Sierra Nevada. So the last part of the rock cycle is once the uplift has occurred or the mountain has formed, the atmosphere goes about weathering and eroding the material, breaking it down into transferable form, rocks, boulders. And this is where the work of the rivers come in to carry that material back out to sea, where it will form and stack up into sedimentary rock, and then go through this whole cycle again. So this is just a real brief overview. The main points are that the Earth's crust goes through this rock cycle in the time frame of hundreds of millions of years, and that rivers do a lot more than just move water. They actually do the work. They're like a giant conveyor belt, taking weathered mountainous material rock and moving it out to sea as part of the hydrologic cycle. And how they move the bed load is real interesting. So this is a diagram straight out of one of the references in Unit 4, and it takes a large river system. You could say this is like the Sacramento River, starting up in the uh, Shasta area, and the headwaters there, the Sierra Nevada, and going and discharging out to the delta and ultimately to the sea. So these large river systems, you can think of them as occurring in these three zones: headwater zones, where the bedrock is broken up and you get the strong rapids, class 4 rapids, moving big earth material; a transfer zone where the rivers are moving the bed load; and then a depositional zone. This would be like the delta. So roughly for the Sacramento River, this would be like the delta where the water is slowing down and discharging and dropping its load. Here would be the foothills, say Auburn, where it's moving bed load in a big way. And then up here in the headwaters would be, the steep part of the mountain range. Uh, this is also out of the manual there that's in Unit 4. I'm not going to be asking more questions about this. My intention here is just to introduce you to this concept to see if you're interested in pursuing it further. But the point of all these squiggly lines really is that these rivers have, they perform very systematically. And so as you go down a river from the headwaters to the discharge, you'll find that the channel width increases in a very systematic manner. The channel depth increases. The discharge of the river increases. The bed material and the grain size that the river is carrying decreases. And the slope looks kind of like this. There's a lot of information, but it's a really interesting way to look at streams. So again, I encourage you to read that reference if you want to dig in further. And another big concept about stream system is this idea of a graded stream. And again, we're looking here at this what's called a cross section. So here is the entire length of the river from the headwater out to where it's discharged to the ocean or a bay. And here's the elevation. And when you look at a river like this, certainly a big mature river, it will tend to form into this profile, a certain shape. And it is, the text here describes it. It's a stream, it's graded stream, that is a stream that has formed this shape, is one in which the channel slope has adjusted so that the velocity of the water is just enough to transport the sediment load. It's a very different way of looking at rivers, but rivers up in the mountains are steep. You could think of it because they need that slope to carry the bed load of the mountains, big rocks and boulders in a sense. Here, let's say with the American River, let's say uh, you would be here in Auburn, let's say down here where the profile is, the slope is not as steep because it doesn't need to be to carry the load that the river is carrying, mostly sand and pebbles and rocks. And then finally, at the bottom of the river, where it might be discharging to the Sacramento River, it's a very gentle gradient. And notice there that the load that the stream is carrying is finer grain material that doesn't need as much slope. It's a very different way of looking at how rivers work, but it's very interesting, and it's a field called geomorphology, in this case, fluvial geomorphology. Here's just another image of the same concept. And here is again at the conceptual level, when a mountain range uplifts, and maybe there's different earth materials with different strengths and erodibility, you might get the young river looking like number one here, waterfalls and all kinds of places where the river is gentle and then steep. And over time, what the water will do is tend to take this shape of the profile of one and over time turn it into 5 and 6. 4, 5, and 6 would be the ideal graded profile. And what the river is doing along the way is taking this rough shape and smoothing it out to the graded profile. So this waterfall here will dig and dig and dig, and eventually it will smooth this out. And it's all, it's this, it's not like the river has a personality and it's trying to do something, but you could think of it that way. The river is trying to carve a graded profile. And so when you see a waterfall, think about that. If you want to dig into this more, how is the river doing, moving itself and its energy to carve the earth into a graded profile? Because that's what it's doing. Here's another more detailed diagram of the same thing. If the land surface is shaped like this and the river finds itself flowing over this surface, what it will do, it will take the energy that it gets from the steep slope and it will dig into the earth material. And then when it encounters this gentle slope, it will lose that energy and so drop its load. And so therefore it's doing a cut up here and a fill down here. I don't know if those of you that might have worked in construction, you do cut and fill projects, take this slope here and smooth it out. You would dig out this and fill in this part. And that's what the stream does. So over time, you're going to have a smooth graded profile from this original land profile. And this again is to get you to think about the river as a conveyor belt moving earth material in the rock cycle. And the way it moves earth material is along the bed load, where it picks up rocks and they tumble along the bottom. You can imagine faster flows can move bigger rocks, basically. But also, what's sometimes overlooked is all the sediment that is being carried in the water as suspended load, little clay and silt particles that can move along with the velocity of the water, and then also any earth material that dissolves in water will also be picked up and carried down. So there's dissolved load, suspended load, and bed load. So that was, I mean, a very, very brief introduction to that topic. Again, it's not something I'm going to be asking you about, frankly. I just think it's fascinating, and I think it's a really interesting way to think about streams. And the next time you're out looking at a river, uh, think about, you don't have to tell the people you're with, but you could think about, gee, look at this conveyor belt of earth material moving from the mountains to the ocean. Looks like it's carrying sand here. I bet if I went upstream, it would be carrying bigger particles. Again, you could keep that to yourself, but it's just an interesting way of looking at streams. And again, I invite you to study further in geography. Now I want to get back into more of what this class is about, frankly, the hydrology, the water resource, and water and how it collects in watersheds and runs over the surface and gets collected in streams, and we collect it in dams and reservoirs and hopefully recharge groundwater with it. And at this point, I'm hoping that these terms are extremely familiar to you. Infiltration is the water going across the land surface into the soil profile. Percolation is water moving through that unsaturated zone. And then contributing to the groundwater. In this cartoon, the groundwater is this blue color, and the brown color is the soil above the groundwater table. And here is another example, a cartoon of groundwater discharging to a river and causing base flow. So we're going to see more of that in talk number 2, base flow. There's also a term here, interflow, that is, it's a little oversimplified to say that if the water infiltrates, that it will then recharge groundwater. A lot of times what happens is it'll infiltrate and then stay pretty shallow if the slope is steep, and then it'll seep out the banks and contribute to the stream. And then what the next few slides are about is surface runoff. And the second talk is going to be about how you can watch a river respond to rain events based on the surface runoff and the base flow. And I wanted to make sure we cover this topic of erosion. Erosion is really what drives erosion is surface runoff. The energy of the water coming and falling on the land surface, if it doesn't infiltrate, then it does surface runoff. And when water is running across the surface, it can have a lot of energy. And just like with the stream dynamics, when water has energy, it will pick up earth material. That's what it does with its energy. And so you can imagine that this water running over the surface will have a great potential to erode the surface. And I had one conversation with a student already about this. Yeah, that vegetation is a great antidote to surface runoff and erosion. If the surface is vegetated, then the plant material will take the raindrop and dissipate the energy of the raindrop, and the roots will allow for that water to infiltrate into the ground, so it prevents the runoff from occurring. And there's a great deal of study and work going on with how agricultural practices can end up increasing erosion by compacting the soil, stripping the vegetation. And it's real important for agriculture because the current practices we have involve application of lots of nutrients, pesticides, herbicides, and whoops, animal waste. That's like getting into water 2.0 into the stream. So this is why it's something that's important to emphasize. And the basic, these next few slides just walk through the basic progress of erosion, starting with weathering of rock, and so that you have soil or what they call regolith, which is just broken up rock and soil, and then starting with the rainfall hitting on that soil material, loosening it, and compacting it, and causing the water to again use its energy to carry that soil across the surface. So these are pretty famous pictures. Maybe you've seen them before. But if the rainfall is allowed to fall directly onto the surface, then that energy that it has is used again to pick up earth material and start to carry it away. This would be as opposed to if the land surface here were covered with vegetation, leaf material, even detritus, like duff, like a layer of pine needles or something like that, that would prevent this from happening and allow more of the water to infiltrate. And so after you get this compaction and the rain splash, and you start getting water running across the surface, it'll tend to form sheets, and the sheets of water will tend to combine and form rills. And so the energy of the sheet, all the water in the sheet combining to a rill gives it even more energy to dig and erode soil. So this is some pictures of sheet erosion, just water running off the surface. And I think you can get the idea that, hey, this is not such a great thing to happen. We'd much rather that this rain infiltrated, recharged the groundwater, and seeped out gently over the next years to feed a stream. What's happening here instead is that the rainfall is hitting the ground, not infiltrating, running off, taking its energy, picking up soil, and dumping it into the creek. And when we look at hydrographs, we'll see that the creek will then rise quickly and drop off, which is not helpful for a good creek habitat. The creek would much rather have slower flow seeping from groundwater and steady flow. So this is just an example of erosion in an agriculture setting, picking up the soil, but because of industrial agriculture, it's also picking up nutrients, pesticides, herbicides that are attached to the soil particles, going into this nice brown little river here, and that's going to discharge into another river. And when we get into the water quality section, we'll be talking about this kind of pollution in quite a bit more detail. So stay tuned for that. These are just pictures of rills. When you have sheet erosion, water tends to accumulate or combine with itself to make these channels. It doesn't stay as sheet flow forever. It does tend to form these channels, which then further dig in and concentrate the erosion until you get to the point where you've got gullies. So these are pretty dramatic examples, but you can see these if you were hiking around the hills, finding fresh cuts of erosion. If you see something like that, think what's going on upstream of here that is not allowing water to infiltrate and causing water to accumulate and dig in like this. And this is one of my favorite pictures. I mean, it's a little depressing, but it gives you an example of the difference between having even a thin layer of vegetation on the ground surface versus not. So, these are steep, deep gullies that are digging in and removing the topsoil and loading up the downstream river with a bunch of sediment because this vegetation was cleared. And here it looks like there's attempts to interrupt that process. So here the vegetation has been cleared, but you see these shapes here. They're contouring the hill, maybe putting in some swales doing something to take the water that's running off and slow it down so it doesn't go crazy here and accumulate in rills and gullies. So that's actually what I wanted to cover in concept, um, surface runoff and erosion, and again, the conceptual handling of rivers and the graded stream concept. And in part two of this talk coming up will be more of the straight hydrology of streams.